last time I gave you a brief introduction to Wolfram Cloud. What we'll do today is we'll go to Wolfram Cloud and start implementing some of the things. Today is first technical prelims. So what we're going to do is we'll learn basics of few of the functions and see how it's implemented in Mathematica. Once you have opened your Wolfram Cloud Mathematica file, you can go ahead and compute something to test that you're online and it's working. Once we're here, today's objective is to discuss three particular functions. One of them is plot function, the other one is table function, and the third one is manipulate function. Today's lecture we'll call as technical prelims. So we can simply go ahead and introduce a format here using the format toolbar. I'll introduce a title. We'll say call this as technical prelim 1. So technical prelims will introduce you to Mathematica functions. They'll be basically understanding how to implement the functions. The technical prelims will not include any discussion about physics or mathematics. They will just be understanding how to implement Mathematica functions. So today we are going to talk about plot function, table function, and manipulate function, because this is something we require for the next session. So let's go ahead and start with the plot function. So at this point I can go ahead and introduce a section, plotting using plot function. Plot function is a function in Mathematica which allows you to plot graphs. So we'll take a simple example. As always in Mathematica, this is the name of the function and the arguments of the function are put in the square bracket. So I've created a pair of square brackets, and inside that I'm going to put my function. All the Mathematica functions start with a block letter. So in this case I want to plot sine function, and sine function again is a function in Mathematica, starts with a block letter S. Then again the arguments of the sine function will be in these two square brackets. As you hover your mouse over these square brackets, you can see which brackets are closing which pair of bracket. So in the sine function I'll go ahead and write sine of x, and then I'll say I'll plot this from x equal to minus 10 to plus 10. Now note the way I've given the argument over here. This is the second argument of the plot function, and sine x is the first argument of the plot function. The two arguments are separated by a comma. The second argument is specifying what is the name of the variable in which the plot has to be made and what is the range of that variable. So here the variable name is x, and this x matches with the x over here, and the range, the minimum value is minus 10 and maximum value is plus 10. So we are going really very slow over here so that we can understand some of the basics. Since Mathematica is a symbolic programming language, I can put a sign y over here and call this y, and that doesn't change anything. It means the same thing. At this point I'll go ahead and evaluate. For evaluation, I told you can click on this little gear icon over here and you can say evaluate cell, or if your keyboard allows it, you can press shift plus return or shift plus enter on your keyboard. So when you plot a sine function, this is what we get. And as I said, you can call this as anything else. You can call this as a, and that's perfectly fine. You'll get the same result. So this is a plot of the sine function. At this point I want to compare this function with let's say another function. Let's say I want to compare this with cos function. So I can go ahead and expand the first argument of the plot function, convert it into a list by enclosing sine of a inside curly brackets and then put a comma and say cos of a. So now what I'm asking over here is I'm asking Wolfram language to plot sine of A and cosine of A for A between -10 and +10. I'll go ahead and press Shift Enter, and I get two plots. And as you expect, the sine function and cosine function are shifted by just by a phase of pi. So you see that cosine function in orange over here peaks at x equal to 0, and sine function is vanishing at x equal to 0, and sine function peaks at pi by 2, which you don't see here. But what we'll do is we will make this plot a little bit bigger so that you can see that. We'll say we'll give an option image size large. Now you can see that this is 5 over here, so this is approximately pi by 2. But to do that more accurately, you can control your ticks and other features of this plot. As we go along, I will show you how to do those things. But for now, I will, in order to make sure that blue is sine and orange is cosine, I'll add another option which is called plot legends, and in the curly brackets I'll say this is expression. When expressions, when I execute it, it shows me that it adds a legend over here and says that sine A is in blue and cosine A is in orange. Okay, so this is just very brief, starting with some of the Mathematica functions. As we go along, we are going to learn more and more about this. Let's go ahead and explore another function called ListPlot. So let me add that to my list over here. Okay, let's go ahead and discuss table first, and then after table we'll go ahead and discuss ListPlot. Now table is a very powerful construct or powerful function. It allows you to construct a table of items. So for example, if I say table n, and then again in the curly brackets I say n goes from 1 to 10, see what happens. I simply get a list of items over here, list of numbers from 1 to 10. This is essentially what this is doing is I'm saying that I want to take n, I want to take this function, the first argument of table, and execute it for n equal to 1 to 10, and then pack all of that into a list. A list is anything that is between two curly brackets. So for example, this is same as 1 2 3 4 5 6 7 8 9 and 10. To create this list, I have to type it manually inside curly brackets, or I can create a very large list by simply executing a table command. You can also think of table command as something that generates an array of something that you want. So let's go ahead and play around with it. Let's go ahead and say I want a table of n square. So I can simply say the first argument of table function is n square, and give me first 10 squares of integers, and as you expect, you're going to get 1 4 9 16 25 and so on. We can make it more interesting. We can also say I want n factorial. To get a factorial, all you have to do is put a factorial sign over here, which is the exclamation mark, and you'll get n factorial. You can easily check that this is for the small numbers. You can easily identify that this is actually n factorial. So table command allows me to generate a list of arrays, and not only that, it allows me to do list of numbers. It allows me to generate list of arbitrary expressions. For example, I can say I want a table of sine of let's say n pi by 2. So n pi by 2. and I want n to go from 0 to 8. So n equal to 0, you expect sine 0 is 0, n equal to 1, sine pi by 2 is 1, n equal to 2, sine of pi is 0, and so on. So now you see you get the sequence of numbers corresponding to sine n pi by 2. If we wanted to do this symbolically, we could simply maybe put a symbol pi. If I do that for the symbol pi, I again get, because the system recognizes this as pi. Okay, I think it's better to type pi like that, because pressing the escape key takes me out of the full screen. Let me take another example. I can generate tables of plots. So inside the table, I'll put the plot. Let's say plot of sine nx. Should put a space between n and x, because I want to make tables of sine of 1x, 2x, 3x, and so on for x lying between -10 and 10. But I want to take n to go from 1 to 4. So that means it's going to generate me 4 plots. In fact, it's going to be an array of 4 plots. Seems like there's some error. Oh, sorry, I forgot to put a comma over here, and this should have been x. Okay, so let's go ahead and try this again. There we go. We've got an array of 4 plots. You can see by clicking on this. This is my first plot for sine 1x. This is plot of sine 2x. This is plot of sine 3x. This is plot of sine 4x, and they are all enclosed in a pair of curly brackets. This is where the curly brackets open. This is where the curly brackets close, and I've got 4 different plots. Okay, let's go ahead and go back to n factorial. Okay, so we have got table of n factorial for n equal to 1 to n from 1 to 10. I'll go ahead and assign this array to a variable. This time, for that I'll use an equality, and I'll call my variable to be, let's say, factorials. So factorials, I'm going to assign factorials, the variable factorials, the value of the table n factorial from n equal to 1 to 10. Notice that the variable right now is undefined. It has not been assigned any value, so it appears in blue. The moment I execute this by pressing command plus enter, shift plus enter, this factorial turns into a black, which means this variable is recognized by the system. Next time I actually type factorials, not only that it recognizes, it also gives a suggestion. Over here, I can click on this, and then when I execute it, I'll just get the same array that the value it has been assigned to. At this point, I would like to make a plot of this. So I can say that plot this, but I cannot use the plot function, because plot function works for functions with whose argument is some variable x. But for over here, this is a list of items, so I'll use ListPlot, and I'll enclose factorials, the array inside the ListPlot. When I make a plot, I get a bunch of points. You have to look a little bit closely to see the points over here. There's a point here, there's a point here, there's a point here, and it appears that most of the points are lying on 0. But look at the y-axis. The y-axis values are so large. Let's go ahead and give an option over here. Let's say joined is true, which essentially will join all the points. So now you can see see this blue line, which is showing how the n factorial grows with n. Now this is n factorial grows very fast with n. You can see from here that for n equal to 9, the value corresponding to n equal to 9 is much larger than value corresponding to n equal to 8, which is much larger than n equal to 7, and so on. This is what is expected. You see that in the table over here. This is something not very exciting. So what we'll do is we are going to take logs of n factorial, because log of n factorial will not be as large. And when I take log of n factorial, I get this array. Mathematica decides to simply write this as log of that. That doesn't really matter to us. What we'll do now is we'll make a plot, list plot. And now you say, see, log of n factorial actually grows much more slowly. The y-axis is not as big. And now you can actually think of comparing this this quantity with something. As a tiny exercise, let's think about comparing the following things. We'll compare 2 to the power n. We'll compare 2 to the power n e to the power n. Sorry. Let's say n to the power of some p, where p is a number, e to the power n, which is an exponential, or let's say p to the power n, and n factorial. Which one of these do you think grows the largest or grows the fastest as we increase n? This is something we can simply test out by plotting. So what we'll do is we'll generate three arrays, one for the factorials, one for the polynomials. N to the power p is a polynomial, p to the power n is an exponential, and n factorial is factorial. So what we'll do is we'll say we'll generate our first array, polynomials, for a fixed value of p. So for that I'll say table n to the power p. We'll choose p equal to 4. Just as an example, we'll choose p equal to 4, and I'll say n goes from 1 to 10, and we'll go ahead and execute that. So this will generate me an array which I've named polynomials. This is what the numbers look like. Next we'll go ahead and say exponentials. Exponentials will be, we can, if you want, we can copy this from here, or we can simply go ahead and say this time 4 to the power n. So n is in the exponent now, and we'll say n goes from 1 to 10 as before. And now you see we get another sequence of numbers, and these numbers initially they're somewhat smaller than from these numbers, but eventually they become much larger. And finally we are going to take factorials here, and we'll say n factorial, and we'll say n goes from 1 to 10, and that'll generate me the factorial sequence. Now I want to make a list plot of these, and I want to make a list plot of all of these simultaneously. For that, in a curly bracket, I'll include all 3 of them, which is the way to make a list plot of all of them on the same plot. Exponentials, and factorials. For some reason this is in some strange blue color, but that doesn't matter. We'll go ahead and plot it, and you see the dots are in 3 different colors, which is a little hard to see, so I'll say that joint is true. And to understand which color corresponds to what, I will also go ahead and add plot legends option. So in order to create this arrow, I press a dash and then a greater than sign that creates an arrow. Plot legends in the quotes, I'll go ahead and type expressions, which means that give me a legend for this plot with the expressions. Well, that wouldn't work because this is there's no expression for these, but this is simply data. So we will say that plot legends are, the first one was polynomial, the second one that we use in the array over here is exponential, and the third one is factorial. So blue line is for polynomial, which is the slowest growing function. Then the orange line is for exponential, which appears to grow really fast. And then finally third one is factorial, which eventually picks up and grows very fast. Now, since I'm not plotting everything, it's unclear what's happening, how they're competing, because I have not plotted what's happening beyond 8 for these two functions. So to get that, I'll add another option called plot range, and I'll assign it a value all. Let's see what happens with that. There we go. So polynomial is pretty much invisible because polynomial growth is very, very slow. You're comparing this 10,000 with this 3 million. And then exponential is the next one, and eventually the factorial picks up. Somewhere in the beginning, exponential was leading the factorial, and then the eventually factorial growth picks up and becomes faster than all these three functions. So this was a quick example of how we can compare these various functions. Let's go ahead now and look at the last item in our list today, the manipulate function. The manipulate function turns out to be something very useful. What it allows you to do is, it allows you to control a parameter and vary it by moving the sliders. So suppose I say n, and for the first argument of manipulate, and for second one I say n comma 1 to 10. Let's go and see, execute it and see what happens. Yeah, okay. So now you see the output of manipulate is this frame where I see a slider marked with n and a value printed over here 1, which is the value of n. If I click on this little tiny plus button over here, it shows me the value of n and shows me a plus and minus sign, which says if I click on this will increase n, and as a consequence the value of n will change here, and correspondingly the value of n will change here. This is the value of the parameter, and this is the value of the display. Right now the parameter that we are varying is also the value of the function that we want to display, so I'm getting the same value over here. Let's go ahead and make this n squared. Execute it. I can also go ahead and just move the slider, and as I move the slider, you can see this number changes. I can click somewhere on the slider, the value of n becomes something is wrong with here. Yeah, value of n is 3.82, and you get 3.59 corresponding to that. For n square, I change this, value of n changes to 6.02. I get a square of that is 36.24, and so on. Now this is not very exciting. What we'll do is we'll replace this function with a plot of sine of nx for x between minus 10 and 10. Let's go ahead and execute that. This time output of manipulate is a plot which is inside this frame along with the slider for changing value of n. Since the first value of n is 1 here, the slider is initialized, the value of n is initialized by 1, and I'm getting a plot of sine of 1x. I never said what is the value of n I wanted over here, but manipulate automatically initializes the first value of that is given for n. And when I do that, I can now go ahead and slide the slider. As I slide the slider, the value of n gets updated and the plot gets updated. So what happens when I change n? I'm essentially increasing the frequency of sine function, and the sine function is oscillating more and more rapidly. Very well. So this was a little bit about manipulate function. If you want to initialize n by a different value, let's say 3. So when you do that, now this will allow n to be initialized by 3, and you see the slider is set at n equal to 3. You can click on this small plus button to see that. Now as you increase or decrease, as you change the slider, you can change the value of n and correspondingly the plot of the function. This was just some prelims to get you to understand how some of these functions work in Mathematica, and in our next lecture we will use some of these constructs.